If you struggled on that, hopefully today's lesson will give you a little instruction as to how to get it done. And then we also have the match graph concept builder, not concept builder, but Canvas quiz. We started worksheet 1 last class. We did pages 1 through 3. Some of you were really productive and got it done in class. We're going to finish 4 and 5 today. And if you don't finish it in class, it's homework. The answer key for that is going to be on Canvas also, but make sure you go through the steps of trying to do it yourself before you get onto Canvas and check your answers. The warm-up. I want you to do this on your warm-up page. Draw a nice big line across the previous warm-up so that I know exactly where to stamp for warm-up 2. And this one, it's basically a good review of graphical analysis for position time graphs. Very similar to worksheet 1 that you guys worked on. And also, it is going to be part of the quiz that is going to be next class. So we had a long weekend. I want a good reminder of how to calculate position time, how to analyze a position time graph, so you're drawing the position time graph yourself, and then how to use those calculations. So let me have you in the meantime, as you're working on your warm-up, make sure that you are pulling out worksheet 1. There was also a set of notes on distance, displacement, speed, and velocity. You're supposed to take those notes on a separate sheet of paper. Pull that out for me as well. And then you did get your stamps from the last warm-up, correct? Yes. And I know a lot of you already got your stamps for the worksheet. So if you already got your stamp for the worksheet, then you don't have to pull that out. If you need a stamp for the worksheet, make sure to pull that out for me. And in the meantime, I am going to be checking attendance in the cell phone doc, so make sure your cell phones are up there. We're going to walk through the problem-solving part. Most of the time, I'm going to have you figure out the equation yourself. In this scenario, I gave it to you. So all it is plugging in a basic algebra. So it says to predict the position when the horse is at, where the horse is at in 22 seconds. Position is equal to the velocity times the time. It starts at 0, so it's simple multiplication. Did you guys get 264?
Yes.
Any questions on problem number 1? All right, the next one is solving backwards. So there's a little more algebra. They give you the position. You need to solve for the time. It still starts at 0, but this time we have to solve backwards. So understanding how to do the algebra, and I saw a few mistakes like this on the test, so I want to emphasize whenever you are solving this situation. Beautiful. Perfect. That's great.
Should I label which one's horse 1 and horse 2?
So in this scenario, we've got 150. We subtracted the 0 over it. It basically cancels itself out, and then divide the 12. I had a lot of students subtract the 12. Remember, 12 is being multiplied by time. So the opposite of multiplication is division. This student even reduced the units, which is beautiful. Do I require the units on the work when you take your quiz or your test? No. But do I require the units in the answer? Absolutely. So 12.5, do you guys agree? Yes. All right. So we have the graph. This one was the hardest one. The long weekend, it's hard to recall exactly what to do, but Sebastian did an awesome job. He also did a good job of putting in the units, evenly spaced number values. But what should I add just to make it that much better? You gotta label your axis. So time and the unit in parentheses. Position and the unit is, what is it, meters? Meters instead of centimeters. Okay, so in this scenario, we've got horse 1. They start at the same position and they both run at constant speed. The horse 1 starts at 1 starts 1 second after the starting bell. So I want you to notice this. They both start at the same position. I didn't tell you what position, but Sebastian decided he was going to make them start at position 0. Horse 1 starts a second after. So he doesn't start till time 1 second. And then they have constant speed, meaning the slope stays the same. So I didn't give Sebastian any ruler for this, but we want these to be nice straight lines. And then it says, after 5 seconds, horse 1 passes up horse 2. So here's 5 seconds, and it's not perfectly lined up, but this would be where our 2 horses end up crossing, right here at 5 seconds. Horse 1 passes, horse 2. Do you guys agree?
Yes.
Any questions? All right, I have a really important question for you. Is there any point in this graph where horse 1 and horse 2 have the same speed? I see Ethan over there shaking his head. What do you think, Ethan? They're not parallel. Slope represents speed. Slope also represents velocity. What's the difference between speed and velocity? Do we need a little warm up, Grace?
Speed doesn't focus on direction or velocity.
Speed doesn't focus on direction. Velocity focuses on direction. What direction are these horses going in? Forward. Backward would look like what? What would a backward moving horse, Kaylin?
Yeah.
It would be going this way. This is my backward motion. Forward motion is a positive slope. They never have the same velocity. Velocity is representative by the slope of a position time graph. This is really important. And the velocity is never the same because they are never parallel. Questions, comments, concerns? Okay. Moving on, I want to go over some important concepts. You took some notes on scalars and vectors, distance and displacement, position, and what was it? No, speed and velocity. So with those notes, I just kind of want to go over this concept with you. So let's start with little video. Did I already show you this video? Did we already go over the scalar versus vector chart? Okay, that was my other class. Careful. Okay, let me get the video going. Pay attention closely. This is very technical information. I need volume. Start over. All right, so we've got a vector, which is direction and magnitude. Who can tell me what magnitude means? Oh, come on. Magnitude? What is that? Speed is a type of magnitude. What does magnitude represent? Vocabulary. The number value, your numerical value of your variable And a scalar is just the magnitude, just the numerical value. Knowing that vocabulary is going to be important. Vector has the numerical value, it has the magnitude, but as I don't know who this character is, but as he stated here, it also includes what? Vectors also include Ava and direction. So let's just go through all the different scalars and all the different vectors that we established in this class. I'm going to start with our forces unit. Is force a scalar or a vector? How many of you guys think it's a scalar? How many of you think it's a vector? I want to see armpits. Let me see your armpits. Good. It is a vector because remember, we can have a positive force going right and a negative force going left. So force is a vector. The other thing we talked about was mass. Is mass a scalar or a vector? How many of you say it's a scalar? Half. How many of you say it's a vector? How many of you say it's a scalar? I want to see armpits. You're right. Mass does not have direction. It is the amount of matter an object is made out of. You can't have negative mass, right? Let's talk about F equals ma. A stands for acceleration. Is acceleration a scalar? How many of you think it's a scalar? How many of you think it's a vector? Acceleration is a vector. Acceleration includes direction. We'll get into the details in terms of what direction it points in when, but it is directly proportional to force. And if force has direction, acceleration has direction. If force is pointing in the positive direction, so is acceleration. Okay, now let's get into our position and kinematics equations. We talked about position. Position is where your horse or your object is at a specific point in time. Does position have direction? Would it be a scalar or would it be a vector? How many of you say scalar? Position is a scalar. Got a few? How many of you say it's a vector? I got it. How many of you did not vote? Be honest. All right. So let's think about our lab with the monster truck. We started at 0, we went to 100, and when we moved backward, we started at 100 and we moved towards 0. Did any of you in the backward direction get negative positions? Did any groups get negative positions? Yes. We can move in the negative position if we start backward or behind our starting position. So position is a vector, and we represent position by x. I'm going to put the variable there because x is not usually or easily associated with position. And then we've got something called displacement. Displacement is the change in position. So I'm going to introduce you to a new variable. Not a new variable, but a new symbol. Delta. Delta means change. So when I'm talking about a change in position, I'm going to represent it by delta x. First of all, you guys did notes on displacement. Is displacement a scalar? How many of you say yes? Is displacement a vector? Very good. So displacement is change in position. I'm going to represent it by delta x. Basically, it's the final position, x final, minus the initial position. You just take the subtraction between the two. That's part of your position time homework tonight, so you want to pay attention closely. What about distance? If I say I want a distance of 100 meters, does that include direction? How many of you say it's a scalar? How many of you say it's a vector? If I say I want a distance of 100 meters, Does that include direction? Does not. So this is a tricky one. Distance is just the total value of how much you've traveled. And when you're traveling down to LA or you're going down on a road trip to Disneyland, you're taking winding roads. They will tell you in the signs the distance in miles it'll take you to get there, but it's not going to include direction because your direction is going to change as you travel all the way down to LA, to Disneyland, wherever you go. So distance is not direction. It is the count, like on your dashboard, the total count of how many miles you've traveled. Okay, let's go into speed and velocity. Speed, is that a scalar or is that a vector? How many of you say scalar? Does speed have direction? This one I was hoping was an easy one. Does speed have direction? Is it a scalar? Yes, it does not have direction. We just established this. Speed doesn't have direction, but velocity does. Velocity is represented by V. So I want you to keep in mind what variables we use in physics. We always use velocity. Sometimes I interchangeably say speed, but direction is going to be important. Positive velocity means you're moving forward. Negative velocity means you're moving backward. Displacement is change in position. X is position, A is acceleration, and capital F represents force. Questions? All right, let's get into the fun stuff. So we talked about constant velocity. You did a monster truck lab, and the monster trucks moved at a constant speed. Nice straight lines on your graph. We also understood that the slope of a velocity time graph would give you your, the slope of a position time graph would give you your velocity. If I were to draw velocity graphs for constant velocity position graphs, what would those velocity graphs look like? You just did a lab on this recently. You just did homework on this recently. If I were to ask you to draw a velocity time graph for, and let me just grab my eraser. If I were to ask you to draw a velocity time graph for these two horses, here's my velocity, here's my time. What would those two graphs look like? Can someone tell me the general picture, the general shape? They would be two straight lines. Straight sloped lines, straight parallel horizontal lines. So I would have two straight lines like this. Which one would be the top line? Horse. Whichever one what?
Started later.
Whichever one started later? Would it be horse one? Is it because horse one started later? It's because why? It has a faster slope, a higher slope and a faster speed. So horse one would look like this. Horse two will look like this. Okay. Here's what we're doing in our lab today. I want you to pull out your orange lab. And there aren't too many sessions to practice through, but what I want to point out is, and that's simply because we didn't get the back page printed out, but that's okay. What I want you to do is go through these practice problems, and then I want you to practice the other scenarios in your Match That Graph lab. So first, before we even get started, I want you to look at your roles. Tech managers, I want you to pay attention closely. First thing we're going to do is we're going to jump into a Match That Graph simulation. So I want you to look up here and follow along with everything that I'm doing on my computer. Let me just switch this out really quick. I want all my tech managers' attention. And you are going to my materials managers, you're gonna grab a bin. It's got a ring stand, it's got a motion sensor, and it's got a USB link. The USB link plugs into your computer. And then once that's plugged in, your tech manager is gonna open up a simulation that looks like, and this is all in your Canvas, but it looks like this. It's a person walking on a little graph, and it'll open up this position time graph. You've got your motion sensor. So materials managers, pay attention closely. Your motion sensor is going to detect your motion. There's two parts to this motion sensor though. You've got a part and a person position. It's detecting your motion. So you want to keep it on person, make sure it's on the right tab. And then also you want to make sure that whoever is moving in front of the motion sensor has the motion sensor right around their chest so that it reads your position accurately. So you can adjust it up and down based on who's testing. Every single person needs to run through this position time graph together. The other thing, and this is optional, my first period decided not to use this, but it was to their detriment. You've got meter sticks. You've also got position in meters on your graph. So feel free to use this. The nice thing about this simulation is once you start it, let me open this up a little bigger. Once you start it, it's going to give you 3 seconds just to find the right position. And then you want to move your body to match this graph. So I got an 89.14 score. I purposely did badly just to give you guys a little confidence boost. So your goal is to beat this score. You want to make sure you're starting at the right position. It gives you 3 seconds to get there, and then you're going to travel along that path. The competition at the end is going to be some of these random graphs toward the end, so I encourage you to practice all of them. You've only got 4 on your worksheet, but I want you to, if you have done all of the stuff on your worksheet, I want you to walk through this graph on your own. So first thing, we've got number 3, which is position. I want you to, before you even grab your materials, get in your groups and draw what you think the velocity time graph would look like for this position time graph. And then when you go through each graph, for example, we don't have number 2, right? Number 2 is not on here. So if I were to draw a velocity time graph, what I think the velocity time graph should look like for position number 2, I'm going to check it by clicking on position, and it'll give me the velocity graph for that position time graph. So first step, get into your groups. Look at the position time graph and make a prediction of what your velocity time graph would look like. Second step, open up your simulation. Tech managers are going to click on the options, find the graph that you're supposed to analyze, and then you're going to click on position and then check velocity. So this is just to check. All of your tests are going to be done in the position option. Okay? Your velocity option is only to check your answers for graph number 2. The next step is describing your motion and to draw a motion map. So a motion map, I'm going to show you when we did Unit 1 on forces, we had motion maps that looked like this. Little swish marks to show motion. What do those little swish marks represent if they were equally spaced apart? Grace. Constant speed. In a motion map, your constant speed is going to look like a set of dots. It is the position of that object over time. So this is constant speed. What would happen if I had a position, or what would happen if I had a motion map that looked like this? The dots got closer and closer and closer and closer. What would that motion be described as? What is it, Roberta? It's slowing down. And then the opposite, if it was getting further apart, it'd be speeding up. Now, here's the problem with the motion map. I don't know what direction this object's going in. I'm assuming it's going in this direction. But it could be speeding up in the opposite direction. So in a motion map, you've got a set of dots to represent its position, and then you've got something called velocity arrows. These velocity arrows give you an indication of which direction the object's going in. It's going to the right, not to the left. So I want you to do a motion map to describe your motion as well, and then we'll go a little bit back over motion maps later. Any questions? First step, get into your groups. You're going to go through position number 3, position number 1, position number 6, and position number 4. And then you're going to guess what the velocity time graph looks like and then check using your match that graph simulation. Remember, the match that graph simulation looks like the person walking on a number line. And then you're going to start testing out your velocity. What is it going to look like? Always keep it on position. What is it going to look like? What is your motion going to be if you're testing out this type of scenario? So if I'm moving here, I want to make sure that my path follows this line. And then you're going to determine toward the end of the period who is going to be the person to test in the competition. Who was the best person that got these graphs correct? Is you were supposed to check your velocity from what you thought it should be in this graph. So for the first one, it was number 3. Your velocity would have been a straight line, right at 0, horizontal line, right? Then we've got velocity graphs that, for number 1, this one was a horizontal line, but it should have been on somewhere on the positive graph. All of our graphs had horizontal lines until you got to problem number, so this is problem number 6, right? You've got a positive slope and then it got steeper, so a higher positive slope for position graph. And then the last one was the harder one where you actually had a curve. So we didn't talk about this type of graph yet. What is it? Number 4. But can anyone describe to me what type of motion you had to do to get this graph to look perfect? What type of motion does that look like? How would your body be moving in that graph? It will be accelerating. You start slow and you speed up. So that's an acceleration graph. It starts moving faster and faster. The slope, though, changes. So it's not going to be a horizontal line. The velocity is actually a straight line, but with a positive slope. So that's what we use to represent acceleration. In your homework, you're supposed to finish worksheet 1, page 4 and 5. This is where you calculate the slope, which gives you your velocity, and you draw the velocity graph. All of these should be horizontal lines. We're not going to talk about acceleration till next class. The homework for your position time graph in the concept builder is going to have you use the equation position equals velocity times time plus your starting position. This is the equation we came up with in the Monster Truck Lab. Do you guys remember that? It should be final position equals velocity times time plus starting position. You are going to look at a graph, figure out the velocity, which is the slope, figure out the starting position, this is the y-intercept, and then they're going to tell you what the time would be and what the starting position would be, depending on what you have to solve for. So we didn't do this for a while. In your physics helper, it looks like x final equals velocity times time plus x initial. X represents position, And in your physics helper, you also have the graphical representation in words. So here, we've got the equations. You've got your constant velocity equation, but you also have interpreting graphs. And it tells you right there, velocity is the slope of the position time graph. So that's the information that you want to know for this homework. You got finished worksheet 1, page 4 and 5, concept builder, position time graph. Match that graph is just a Canvas quiz. It should be pretty quick. It's multiple, it's matching, so I only give you 3 tries. Beyond that, it's just process of elimination. So 3 chances to match your graph, and then to study for quiz 1, which is focused on analyzing position time graphs like the warm-up we did today, and this homework on drawing velocity time graphs. Worksheet 4, which now I've misplaced. This stuff, okay? Questions, comments, concerns? I know those of you who saw the homework, thought position time was due today. I totally messed up the dates on that. It's really due on Friday, but make sure you do that practice and it's related to those concept builders.